Hello everyone and welcome to Microsoft Mechanics Live. Today I'm joined by one of the foremost experts in quantum computing, Krista Svor, and we're going to attempt to demystify the core concepts around the topic and make it real for everyone. And we're also going to look at Microsoft's contribution in the field, developing a full system approach comprising of three major breakthroughs. First, with the topological qubit, a new way to be able to do quantum computations, also the scalable quantum hardware with cryogenic control, and a complete software stack for programming and controlling quantum computers. But first, please give me a warm welcome for Krista Svor.
Thanks, Jim. Good to see you.
Thanks for joining us today. So, Microsoft has been pioneering some really important breakthroughs in the space of quantum computing. But before we go into the significance of all these innovations, can you help explain what quantum computing is?
Yeah, of course. So, quantum computing is really a big paradigm shift. It's a new and different form of computing that really goes exponentially beyond the capabilities of our best and most powerful supercomputers today. And it's grounded in the principles of quantum mechanics, which underlies the fundamental theory of nature at the smallest atomic and subatomic scales. So with a quantum computer, it's quantum mechanics that really governs how we store the information and then how we process and compute on the information.
So everybody here is probably a computer scientist. So how does this compare to today's computing?
Right. So today, computers, of course, are based on transistors. And transistors are like a switch. They support only two states, like a light switch, with two positions, so either on or off. And of course, this translates to the binary ones and zeros that we ultimately program in. Now, as you need more information with a transistor-based machine and more compute power, you need to add more ones and zeros into your machine, and therefore you're adding more and more transistors in. And of course, we're striving to fit as many transistors as we can. As Satya mentioned in the keynote, we have billions of transistors in the Xbox One X. We're trying to fit as many as possible into a very small chip size, and we're going to hit some physics limits.
So it's a lot of transistors, and now they're getting down to 10 nanometers and even smaller, which is mind-boggling itself. But the quantum chips are going to be a lot smaller, right?
Well, yeah, so we're operating, on a smaller scale in terms of the information, but ultimately, this quantum computer is going to sit in a large dilution refrigerator. But indeed, the information, the way we hold and process information really operates differently. So in the transistor model, you have this on-off switch. A quantum computer is, somewhat more like a dimmer switch. So you can take on both the 0 and the 1 state simultaneously, and that's what we call a superposition state.
So there's a couple ways to think about this, right? So what would it look like, I guess, when you think about binary now versus in the quantum world?
Yeah, so in binary today, if we take 4 light switches, let's say, right, a string of four bits, and we take all the zeros and ones, you work through all the possible string combinations. You can get 16 values with this, 2 to the 4 possible states. But that combination of the zeros and ones, you can only operate on one of those strings at a given time. Now, in a quantum state, let's take 4 qubits instead of 4 bits. Now, these 4 qubits, in fact, store all of those 16 states at once in 4 qubits.
So that means that the quantum computer can have a lot more information and process a lot more information simultaneously. But can't this level then compare to the compute that we might be able to do with maybe a supercomputer and parallel computing and transistors now?
Yeah, it's a great question. So, you think of quantum computers as having this massive parallelism. Now, classically, we could try to achieve that with a parallel computer. But now I need that many more resources, that many more switches, and I operate on all of the possible states simultaneously, but I need 4 bits for every possible string. In a quantum computer, again, I only need the 4 qubits to operate on all of those states at once.
In terms of the way that quantum's working now, we're creating kind of lossless power grids, right?
Yeah, so in terms of the applications of a quantum computer, what we hope to achieve with a quantum computer is to solve truly revolutionary problems, world-changing problems. And clean energy is one thing that we would really strive to overcome, right, and solve. So there, with a quantum computer, we can look at materials and we can study materials that may actually superconduct at a high temperature. And in turn, that would allow us to create a lossless power grid and so forth. And these applications go beyond just materials. We can look in chemistry, look for better catalysts, and then, of course, artificial intelligence and machine learning are other areas.
And a lot of these problems are really, really hard to be able to solve in terms of materials science and all the things that we would do maybe with classical compute. Now this gets a lot easier and a lot more powerful with quantum, but what are some of the ways that people might be able to harness this power then in the future?
Right. So here in quantum computing, we're dealing with these, the very, very small scale subatomic particles that are governed by the laws of quantum mechanics. And so we need a totally different approach to computing and to programming. And we actually have to really learn how to program and develop these new applications and algorithms. It's a totally new paradigm. So at Microsoft, what we're doing is putting together, a full stack approach, a comprehensive approach to enable scalable quantum computing. And that includes everything from the hardware to the software to the application layer. What are the revolutionary applications we're really going to run on this? And to do that, we have to bring together a very diverse team. So we've actually been working in this space for almost 20 years at Microsoft, which is pretty incredible. And I think one of the truly distinct things about our approach at Microsoft is how we've assembled this amazing research and engineering team in labs all around the world dedicated to advancing quantum computing. And we've partnered with academia and universities, and we've brought together a truly diverse expertise. And that's really required to build out this full stack. So ultimately, our goal is to realize a scalable and programmable quantum computer so that we can tackle the world's most challenging problems. And then, of course, with that, ultimately, we envision this quantum computer sitting in Azure, right? So just as we have today in Azure, you can access a GPU, CPU, FPGA, right, as your accelerator options. We envision a quantum computer sitting in Azure as one of your possible accelerators that you can call from the app that you're building in the cloud, and then ultimately, achieve a solution you may otherwise not be able to achieve classically.
That's great. So imagine picking out a VM instead of going for the D series VM or E or F series VM. You've actually got a quantum set of compute that you're working off of.
Right.
So really great to see that and really imagine the scale that you can achieve through all the compute that we'll be able to do with quantum in the future.
Right. So yeah, exactly. I mean, scaling is one of the key things here, right? We want to be able to achieve a very scaled out quantum computer with thousands and beyond in terms of the numbers of qubits. And to do that, you need hardware. So one of the key pieces that we're working on is building out the scalable qubit, the qubit that's going to be robust enough to actually scale to these large numbers. And qubits are inherently fragile. So they have to stay in this cold environment because they want to, otherwise they're disturbed by the thermal vibrations and by temperature, the heat itself. So in the quantum world, qubits are very susceptible to noise. And the type of qubit we're working on at Microsoft, a topological qubit, is extremely robust to noise, which means we'll be able to scale with far fewer resources than other competing qubit approaches.
And there are actually different types of qubits, right? I mean, what makes the topological qubit special and more robust?
Yeah, so this topological qubit, it really is a very distinct approach. And it's extremely robust to noise. And it's robust to noise because the information is actually stored non-locally. So it's stored in a more global fashion, if you will. And because of that, it means it's less error-prone. And with being less error-prone, you can scale up much more easily. So the overhead to achieve a long computation, or a computation with many, many operations, is far, far less, several orders of magnitude less than kind of the resources required if you were using another type of qubit. So the type of qubit and the system we're building at Microsoft is really about reliably storing information and computing on this information and being able to do that at a large scale, long algorithms, lots of operations.
And part of this is in terms of being able to actually operate the compute and do all of that across different temperature spectrums. What does the compute environment actually look like in terms of leveraging that topological qubit?
Right. So here's a great picture. Right at the bottom of this stack of this complete system, we have the quantum computer where the qubits sit, and that's sitting at 0.01 degrees from absolute zero. Right.
Wow.
It's very, very cold, minus 459 degrees Fahrenheit roughly, and then above that sits the cryogenic computer. This is a classical computer unlike any classical computer we've ever seen or developed. And at Microsoft, we're developing this computer. This computer controls the quantum computer, and it sits at roughly 20 millikelvin. That's around minus 452 degrees Fahrenheit, so not a whole lot warmer than the quantum chip. And then beyond that, we sit in this room temperature world, around 70 degrees, and then we're going to program the quantum computer from this temperature. And so we have to build out a software stack and all of this hardware, a complete stack that enables us to scale this whole system to 1,000 qubits and beyond. And just to put it into context, at 1,000 qubits, you're looking at around 10 to the 300 times the processing capacity of today's supercomputers, assuming a petabyte supercomputer.
Wow.
So, it's not like the next generation of supercomputers is going to get you that much closer. This is far, far beyond any classical computing we can imagine. And then we have this software that will allow you to actually harness that power and program quantum applications.
So part of the challenge then in terms of the software, because we've been talking about all of the kind of subatomic particle, the really, really small levels and the size of the qubits and all these things, but you have to make the tools so there's something that people are familiar with, right? So what have we been doing in terms of the software stack to make it something that people can leverage that maybe in the future we'll be able to actually start building the right computation?
Right. So we're engineering this cryogenic system, the quantum chip, the cryogenic control, and then this software stack. And the key there is tools for developers like everyone in the audience today. We want to give you tools to be able to start building quantum solutions and start understanding and developing a generation of quantum applications. And so to do that, we've actually designed a special language, a domain-specific language, that's really designed for scalable quantum computing. So it has some awesome features. It kind of looks and feels like languages you already know, like F# and C# and Python. But then in it, it also allows you access to quantum subroutines and quantum libraries and ways to actually call some of the special properties of quantum computing. We've put this in Visual Studio, integrated it right into Visual Studio so that you have also the kind of environment that you're used to and tools that developers love. And within there, it allows us to do quantum debugging, so you can actually debug your quantum code, which is very distinct to our tool chain. You can visualize the quantum state as it evolves through the program. And you can see in this slide here that you also have syntax coloring, making it more readable and understandable. Now, you can also test your quantum program on a simulator. And a simulator runs on your classical machine and allows you to actually simulate what your quantum application would do. And locally, you can do that on around 30 qubits. Yep. And then we also have an Azure-based simulator that allows you to do that up to around 40 qubits and beyond. And of course, simulating those sizes, they don't sound like a lot of qubits, but realize that's, for every additional qubit, it's double the memory.
Right.
So we're looking at, for 230 qubits, it would require 10 to the 80 bytes, which is more bytes than there are particles in our visible universe. So simulating 40 qubits and 30 qubits is in fact a pretty nice number for the classical machine.
So just a little bit more powerful than, say, simulating a mobile phone through Visual Studio.
Yeah, exactly.
Can we see an example then of what this code actually does? Why don't we walk through what the intent of this code that we're actually showing here would do?
Right. So this code here, this is our new language, and it's in Visual Studio. And here what we're showing is an example of what we like to call the quantum hello world, right? Everyone starts a new programming language writing hello world. Let's do the same in quantum computing. In our case, hello world is really an algorithm for quantum teleportation. So this is one of the basic operations that quantum mechanics gives us, if you will. And so this is the circuit diagram. In quantum computing, you read a circuit diagram like music from left to right. So think of it as the lines being the qubits, and then the gates, the operations. If you're an engineer, electrical engineer, you might recognize this. You read the operations like notes, so left to right, and the qubit information flows through and then evolves under these operations. Now, the corresponding code is on the left, and Alan Geller and his team back in Redmond have really designed this language, as I mentioned earlier, to draw from the best concepts of languages like C#, F#, and Python, and then, of course, bring with it the new concepts of quantum computing. And so here in the code, we're really performing the operations from the circuit shown on the right, and this allows us to send information. So teleportation allows us to send information from one qubit to another qubit, even if those qubits have been taken across the universe. You will still get information from the person holding the one qubit to the other person holding this other qubit. And so that's the code shown here.
It's really great that hello world equivalency in quantum computing is actually teleportation.
Right, right.
So we've moved on from the normal hello world applications that we might be building. So quantum computing, in terms of all the power that it can do and all the things that you can do simultaneously, the syntax looks familiar, all the things that we'll be able to do in the future. What can we do in terms of going beyond that simple hello world scenario that we've just shown here?
Right, so to go beyond hello world, we have to start to bring in some of the key concepts behind quantum algorithms. And in hello world, it actually uses what's called entanglement and superposition to send that message. So when you design a quantum algorithm, the first thing you do is prepare a superposition. So earlier we talked about the ability to have 0 and 1 simultaneously. You prepare all the qubits in a state so that they're all in this superposition state. Then we typically build entanglement in the circuit, in the quantum operation, in the quantum algorithm, by performing quantum operations. And then through this, ultimately, we hope to yield quantum speedups from the quantum algorithm. Now, entanglement that we use, say, in teleportation and all of our quantum algorithms, entanglement is when you take two qubits, so initially they're separate. And then we perform a set of quantum operations on these two qubits, and what it does is it intrinsically correlates the information between these qubits. So, Jeremy, if I give you one qubit and then you go across the universe, and I do something to the qubit I have, it will automatically cause something, a reaction, a state change in your qubit, even though we didn't talk and
we're separated by the universe.
And we're separated by the universe.
Right. So from the compute perspective, I guess that means that we're able to perform operations and perform them on all the different entangled qubits at the same time, right?
Yeah, so it really gives you this amazing correlation, this amazing parallelism inside your quantum computer. Now, with that power, we can explore very complex problems that take, lifetime of the universe or billions of years classically, and we can get solutions in only a matter of days or hours on the quantum computer. But there's another key ingredient that you need to achieve those solutions, and that's called interference, quantum interference. And it's like, when you touch a pool, right, and you create ripples. And these ripples send waves. So remember, in quantum mechanics, we have this wave-particle duality. And so think of just the waves. The waves ripple across the pool, and they start to interfere with each other. Now, some of these ripples grow, right? The amplitude of those waves gets larger. And some actually disappear, some of those ripples. And that's called constructive interference when it grows, and destructive interference when it disappears, when those waves collide and you don't see them anymore. And what we do is we really program the quantum computer with our algorithm design to cause the waves that the solutions are actually encoded in these waves. And we hope to increase the height of the waves for the ones that encode the true solution, and then destructively interfere the waves that don't encode the solution. And then ultimately, we have to measure. And we measure the quantum computer. And what this does is gives me out one of these states, namely one of these waves, with a probability that's proportional, related to the height of that wave. So a quantum algorithm is actually a probabilistic algorithm. You may have to run it a couple of times to get your solution with high fidelity. But ultimately, you're programming this tide pool almost, right? These ripples in your quantum algorithm. And it's a true art to be able to do this well. But when you do, you really get some powerful speed-ups. And in a way, it's a bit like signal processing, right? How you want to filter out some signals and then amplify others.
And it totally looks like it. So you're using basically this as a filtering mechanism, again, at that cubic kind of subatomic level as we're creating these waves, so you can look for, in this case, the constructive interference when you can. So
right.
I know a lot of this sounds very, very futuristic to a lot of people, but how far are we away from seeing true quantum computing?
Well, I think we're closer than you think. We're already engineering these systems, right? And we're already developing the software, as you can see today, right? We already have code that's written, and we're releasing these tools to the developer community. Now, quantum computers will truly be revolutionary, right? They're going to allow us to solve the world's most challenging problems, which is super exciting.
So do you see quantum computing replacing some of the transistor-based computers that we're used to now?
Well, so quantum computers won't replace all of the computers we have today, right? They're really meant to be used for a certain class of problems, problems in material science, chemistry, AI, machine learning. So you won't see them replacing all of your classical computers. It's not going to replace your computer to do email or Word, right? But what a quantum computer is really powerful at is modeling nature, right? So with a quantum computer, we can start to get a better understanding of processes in nature. And knowing just how powerful nature is, I think it's going to be an absolutely amazing future, right? Where we can learn some pretty awe-inspiring solutions from the quantum computer by really learning more about nature and what it's doing around us. And then we can use these things to help optimize models in machine learning, artificial intelligence, health, materials, solving big challenges like global warming and clean energy. It's pretty exciting, and I think the sky's the limit. We're all learning how to use this quantum computer to help solve these problems and problems we haven't even thought of.
Very cool. And some of these problems might take 1 billion years to be able to solve with current compute, but how can people that are watching today explore more of the technology for themselves and really learn more about quantum compute?
Well, we're really hoping to build a community around the development of quantum applications, right? This is new to all of us in terms of what we'll be able to do with a quantum computer. And we need help, we need people's help and insight into what should we use these for. So I encourage developers and engineers to really join our Microsoft Quantum community that we have released today at microsoft.com/quantum. And there you can sign up and gain access to the language, our new programming language that's embedded in Visual Studio. You can get access to the simulator, our debugging tools, and then also a whole selection of samples and tutorials to get started, including the Quantum Hello World example, but also more detailed examples around quantum chemistry and how you use quantum computers in that space, and so on. So there's lots to get involved in, and we're really excited to have a development community grow around quantum computing. And the software tools themselves will be available by the end of the year for free, but you can sign up now to get access and insider information. So sign up today.
So really great to see. Thank you, Krista, for helping demystify some of the mind-bending topics around quantum computing. You've seen entanglement, you've seen superposition, all these core topics around there. Hopefully everybody here got a good idea of what we're doing, and also we've just scratched the surface, so I'm really excited to see what's going to come next. So that's about all the time that we have for this episode of Microsoft Mechanics Live, and we'll see you next time.
you.